So for the majority of the class, what we have done is we have figured out that a lot of systems that vibrate can be represented as harmonic or simple harmonic oscillators. And what a harmonic oscillator is that ODE that we're very used to by now, where we can equate the second time derivative of a function to a constant multiple of that same function. What I just said in math terms is we can express a lot of what we already know as x double dot plus omega squared x equals 0. Nothing new at all. However, there's one x in this problem that we're solving for. It's a function of one object that moves in a very specific way that we're solving for. What happens if we have multiple masses in a system or multiple things that we need to track the motion of? Well, that's what exam 2 covered. And what exam 2 did is it showed us that we can express any number of degrees of freedom as a linear system where we had a matrix for mass, something with a damping constant, and something with some type of stiffness equals 0, where each of these are matrices and each of these are vectors. These two different types of ODEs represent something with a finite number of degrees of freedom. And remember, in this case, the degree of freedom is something that you measure. So for one mass, we would have 1 degree of freedom if it can be measured as a horizontal displacement. That's what we have up here. For here, this is an n-DOF system, meaning that however many masses you have, assuming that they're all one-dimensional motion, that's how many degrees of freedom we have. If we have one mass that can move both horizontal and vertical, that's going to be a 2 degree of freedom system, 2 DOF system. We understand degrees of freedom. However, up until this exam 3 content, we've all been working with finite numbers of degrees of freedom. The systems that we use are called discrete because we can sit there and count all of the little sections that we can break up the motion of the system into. There's a number of masses that we can easily identify. What exam 3 talks about is continuous systems. So we have flexible members, and if we have something like a string just floating in space like this, like if you're in a pool and you're like, ew, somebody's shoelace, what is that? It's kind of hard to break up a specific section of a string and say that it moves in a certain way. There's not really an easy way to put a coordinate system onto this thing and describe how a discrete chunk of this breaks up. So we're going to need a new type of strategy to analyze the motion of a system like this. And so that's where Euler and Bernoulli come in. So with strings and beams, flexible members, which are continuous members, we're going to have to start discussing distributed loads, distributed displacements. So you have something with like a length like this. It's going to have like a displacement that's different everywhere along its axis. And what we can do is we can represent this displacement as a function of x. So however far along we are on the member, it displaces this much. So it's not going to be one function representing one point anymore. It's going to be one function representing the relative displacements of the entire thing along its length. So what Euler and Bernoulli realized is that we can treat the bending of a beam and relate the curvature of the beam at a certain point along its length to the moment at that beam. And so we'll get into that in a second. But they had inspiration from other places in physics. And what we're going to use is a wave equation. So before, we had derivatives of time with our ODEs. But now, since we're going to have to represent something as a function of x, we're going to have both derivatives of x and t, which means that this is no longer an ordinary differential equation. An ODE is a function that has one independent variable. Our PDEs now have two independent variables, x and time. So we're going to have spatial and temporal dependence. And I'm going to skip a long derivation for everybody, and what we find out is if we have a beam like this, right, and along its length is x, the displacement of this beam is going to be called W of x. However, now we have to realize it's not just a function of x, but it's also a function of t. This is important. The function we're trying to solve for is multivariable, and so we're going to need to approach it in a slightly different way. Let's assume that this has no cross-sectional width or height. Let's say this is a one-dimensional object as a line, for now. We realize that objects like these don't really have a density because they don't really have an area. All they have is a length. However, there is a mass to this object because we need it to still hold for Newton's first law. So what we're going to do is we're no longer going to use density in our equations. We're going to use something called mass per unit length. I'm sure you guys are familiar with this. And one of the biggest things that I've seen a lot of people struggle with on homework 7 and 8, and one of the things that I say have really helped me succeed for exam 3, is changing your notation for mass per unit length versus density. So density, as we all know it, is rho, right? And this has units of kilograms per cubic meter. The notation that I learned, if we have mass per unit area, it's a sigma, and then mass per unit length as a lambda. We don't really have to use eigenvalues for this section of the course, so it's safe to assume that lambda, if you see it, isn't going to get confused with anything else. And this is going to have units of kilograms per meter. I'm going to try my very best to stay consistent because my notes have density and that confused me a lot when I was working with it. So, do you remember in statics when we would say that like a load at a certain point on a beam could be represented by P? We're going to use that notation here as well. So, skipping this long derivation, so because I don't have 45 minutes to explain it, the wave equation, this second order spatial, second order temporal equation that we're going to use to analyze these things is as follows. Mass per unit length times the second derivative of W with respect to time is equal to the loading times the partial derivative with respect to space. This is the equation where it all starts. The way we discovered how to quantify the speed of light is we made another type of wave equation relating Maxwell's equations into one single form, talking about interactions between the electric and magnetic field. And the way they described that is sort of using this factor 1 over c squared as a single proportionality constant. And that c is where we had the speed of light from. So they had this is a generalized wave equation. And we use these for systems that depend on both space and time. So if we take a look at the form of both of these PDEs, we see that they're both second order in time and second order in space. I knew I was going to write that backwards. Sorry about that. This really isn't that important. The important thing to realize is that we can declare the speed of wave propagation as the square root of p over lambda. Ignore this for now. This is the important part. Speed of wave propagation.
If we use lambda, is that okay, or is he going to want us to do it in the row? As long as we like define it.
I would recommend using lambda.
Is that okay?
If you are unsure about whether he's going to accept that, I would just make sure you include units and say that it's kilograms per meter. And as long as you know what you're doing and keep it consistent, it should be okay. Because we also have to use like rho in this, and like for actual volumetric density. And so it'll be okay once we do that. All right. So this is how we treat one-dimensional numbers. Okay, this is not working. Hey, please. Thanks.
Is that one bad too?
It's all right. So, how do we even go about solving something like this? You will be asked how to solve a PDE and how to interpret a PDE, and it's essentially just a differential equation for a multivariable function. So what we can do is, the first place your head should go is separation of variables. It's the easiest way to solve a PDE, and thankfully, in our case, is a very valid way to solve it as well. So what we can do is we can declare that this W function is separable, meaning that we can express it as a product of a function only dependent on x and a function only dependent on t. Can we try this one?
Calling it another one.
Buy myself a new set of markers. Oh, beautiful.
You guys get it?
So if I rewrite that, what I can do is, we had two different second derivatives of this function w. What we need to do is we need to go ahead and evaluate these derivatives, and we can plug them back into the PDE. So if I take a partial derivative of w, this is just a generalized w with respect to x, we're going to have to use the product rule. So that's going to be first d second, so it's going to be wx partial wt partial t plus partial wx partial x times wt. It's probably overtly obvious to you guys that this was sort of redundant, but I'm just making sure, like through a rigorous proof. But since we declared that wt is only a function of t, Wt of x, I apologize, is 0. So this term cancels. So now we're only left with partial of Wx with respect to x times Wt. And similarly, if we follow the same logic, the second derivative of w is going to have the same thing happen again. Therefore, it's just going to be a constant Wt times the second derivative of Wx with respect to x. And so we can do this again and say that just replacing the variables, I'm just skipping ahead. It's just equal to Wx times the second derivative of Wt. And remember that we're going to have omegas and w's in this sort of math, so it's important to make sure that you have your notation straight. I'm going to write a w like this every time, and I'm going to write an omega like this every time. This is going to be our, radial frequency, and this is going to be the displacement of the member. So I can do some substitution into that PDE, where we have c squared Wt equals Wx squared Wt partial t squared. Okay. And that was just substituting those second derivatives that I just found back into this PDE. So now what we want to do is separate the variables. So we're going to divide this, we're going to divide everything by Wx and everything by Wt, so that, excuse me, good gracious, essentially we're going to have all of the x-dependent terms on this side and all of the time-dependent terms on this side. Now, these are two separate functions dependent on two separate variables, and somehow they're always equal to each other with a constant proportionality. Now, the only way that's true if these two totally unrelated variables are always the same is if both of them are constant, and they're both equal to the same constant. So now, what we can do is we can state that this side of the equation and this side of the equation are both equal to the same thing. We're just going to call that A for now. And then we're going to declare that A is equal to the square of our frequency. And now with this relation, we can separate one PDE into a system of two second-order ODEs. Now what we'll have is we're going to have 1 over Wx, second derivative, Wx with respect to x equals A over c squared, and we're going to have 1 over Wt, second t with respect to t squared is equal to A. So now we have made this a whole hell of a lot easier by making this into a system of two ODEs. So we have a PDE, and now we have ODEs. You guys didn't take a class on PDEs, or if you did, you're a lot smarter than I did. ODEs are a lot simpler to solve. We can multiply both sides of these equations by the respective denominator. So now we're going to have something that looks a whole lot similar to what we've done in this class before. Okay, so this is a constant, that's a constant, second derivative, normal function, second derivative, normal function. What are some functions that we know solve this ODE?
Exponential.
Exponentials. What else? That's right. Exact same as we've done before for the rest of this class. We have some type of second derivative equal to a constant times that function. So we have x, cosine of x, sine of x. X in this case is interchangeable with t because they have the same form but with two different constants of proportionality. Therefore, let's go ahead and solve the space one. We're just going to go ahead and assume that it's a superposition of sine and cosine, even though exponentials also work. Therefore, we have Wx is equal to a, which is a constant, cosine of a by c squared. No, excuse me. So, since we declared that a is equal to omega squared, and this is omega squared over c squared, it's the square root of this term that goes inside the cosine. Therefore, we're going to have omega divided by c times x plus b sine omega over c times x. Okay. We can check this with our intuition. We have rads per second divided by meters per second, because remember this is a speed. And x is in meters, these cancel, and then we end up with meters. This is just radians, so that's perfect. So remember, the c goes on the inside of the x because we're trying to have only radians inside here. So that's a good way to check and make sure that you're on the right path. Same thing we're going to do for time. Wt is equal to a big C, cosine, just omega t, because we're trying to get it back into radians. This is radians per second, times seconds is just radians, so that's good. Times d, sine, omega t. This omega is the same between these two equations because the entire system acts with the same frequency. Remember how we had one frequency with one mass, and then with multiple degrees of freedom, multiple masses, they operate with the same frequency with different modes, and now this is going to have different functions with the same frequency.
How did you check if the units are correct for the first Wx?
Okay.
How did you check?
So cosine and sine are functions of radians, right? So what we're going to look for is radians. So we have omega, which is radians per second, and we're going to divide by c. C is the speed of wave propagation, just like the speed of light, right? That's where the c comes from, is because it's a speed of wave propagation. So we're going to divide by meters per second, which is the same as multiplying as seconds per meter. And then x is in meters, so that's just meters. These cancel, we're left with just radians. So you just want to make sure that all of your terms inside the sine and cosine evaluate to simply radians. And now, all we got to do, if we are asked to find a total solution to a PDE, is just combine them. We had W was equal to Wx times Wt, and then you would just write out these two equations. You don't have to multiply them together, but you can say it's the product of these two. And then if you're asked to evaluate any boundary conditions or like you're given any constants, just plug in for A, B, C, and D, just like you would for the first exam. So like if you had Wx of 0 was equal to 0, if x was 0, cosine terms go to 1, and then sine terms go to 0, so you find out that A was equal to 0, it would only be sinusoid. And then if you took the derivative of it, like because x dot of 0 was equal to 0, or excuse me, x dot of t was equal to 0, you would see it was a function of t, take the derivative, so you have w dot, and then you would find out that this would be a sine, this would be a cosine, the cosine would go to 1, the sine of 0 go to 0, so you find out that d was equal to whatever your x dot of t equals 0 was. Or excuse me, your w dot of t. Okay. So just a refresher, you're going to be given the PDE. What you want to do is you're going to want to separate the variables, transform it into a system with two ODEs, evaluate the ODEs as you're very well used to, find the functions for the ODEs, and then represent your total solution as a product of those two functions. Any quick questions before we move on?
How did you go from the left part to the cosine sign? Yeah.
So ansatz, which is a type of ODE strategy, where we just guess that it's going to be equal to some constant times cosine of x.
Yes.
So remember from before where we plugged in like e to the lambda t, and then we evaluated it, and then we used Euler's formula to transform it into the sine and cosine. Essentially, you don't need to like remember to prove it on the paper. You can just write this to that because he understands that you understand this. That wasn't a very good explanation. Let me try and rephrase it. You know that this form is a solution to this type of ODE, where you have the second derivative equal to a constant times the function. And then it's just a matter of taking these functions, putting them inside the sines and cosines, and then rewriting the constant in terms of frequency.
In what scenario would we try the exponential? Would it kind of tell us, or would it kind of be obvious based on the equation?
To be honest, I would say it's not even worth your time.
Okay.
Like, even if you were asked, you would just plug in, like, c e to the a minus c squared x,
Okay.
and then you would just take the second derivative, and then make sure it's equal to that,
Okay.
plug it back in there.
Got it. Yeah.
What were the units of A, B, C, and D?
They're just like amplitudes, so they're dimensions of both.
Well, if the inside's radians, would it have to be 1/2?
If I'm not mistaken, they're just scalars.
Wait, is it talking about the?
Like A, B, C, and D, the units.
So it's a function depending on x and t. T is going to talk about if you like had a video of this play over time, you would see that it would sort of oscillate. Like it would get big, whatever the distribution was, it would get bigger, and it would get smaller, and it would flip and get bigger, and then it would oscillate with however type of distribution it was. And all this does is describe what the distribution looks like over x. It's not a function of time, which means that it doesn't really change with time quite literally. It's just going to look like the profile of your displacement.
But could you like do like a quick sketch of what each would look like?
Yeah, so for example, if we had a string that was fixed on both ends, we'll get to boundary conditions very soon. So this is a string, this is x equals 0. We're just going to evaluate the x for now. And if I plucked this string and gave it a sort of vibration, there's nothing else going on here. And so it doesn't really have a reason to excite into any higher modes. So it's just going to sort of look like this, where it goes back and forth between these two in a sinusoidal fashion. So it's like that, right? If you think about a guitar, and you pluck a guitar, and you're watching it, it has the highest amplitude in the middle, and it's 0 at both ends. However, there's multiple modes of vibration for this. So it can look like this, it can look like that, it can look like this, it can look like that, and so on. And we'll get to that in a second. So the important thing to remember for this is you're given a PDE, set it equal to the same constant, system of ODEs, write the ODEs, solve the ODEs, and then plug these functions back into W. Yes?
Why is it omega over c inside of the cosine sine and not omega squared over c squared? Why did you take the
We
square root?
declared that A was equal to omega squared.
Mhm.
This is just an assumption that we're making. We're just stating this is the truth for the purposes of these expressions. So, if both of these are equal to A, and this one is equal to c squared, we would have 1 over wx times the, oh, right here. This right here is equal to A. We divide both sides by c squared, then we have just the A up here divided by c squared. And since we have omega squared is equal to A, it's the same as saying omega squared divided by c squared, and then omega squared.
Right, but
Because
what
it's
is
the second
square root?
derivative, we need the thing that's inside here to be squared when it's the second derivative, if we're using the chain rule.
Okay. Yeah.
So remember how if we have e to the 4t, if I take the time derivative of e to the 4t, that's 4 e to the 4t. And if I take the second time derivative of e to the 4t, that's going to be equal to 16 e to the 4t. You see how it's a squared term out here because I did this twice? That's why it's the square root of whatever is out here inside. Making sense? Okay.
I'm confused about where the c squared comes from in the first place.
In the first place,
Yeah.
so remember that generalized wave equation I wrote out? It's a constant of proportionality from the spatial parts of the function to the temporal parts of the function. It's just a function from like physics that we know describes things that move in waves. And so we're taking that PDE that we had, saying that it's like we have the mass per unit length times the temporal second derivative is equal to the tension times the second derivative of the spatial part. Okay. I don't want to waste y'all's time too much. I want to get to the stuff you'll actually have to do besides like problem 1. Okay. Alright. So we have these functions right here. I'm going to keep these for now. Keep that there for now. Erase these. And then talk about boundary conditions. So in order to fully characterize a solution, we're going to need 4 different conditions / constraints. Because right now, we have 4 unknowns. So these are the x is the variables in this equation, t is the variables in this equation. You'll be able to figure out what the c is and